This is a Perceptron learning to classify data in real time. Just Python and basic math. By the end of this video, you'll understand exactly how this works. But first, why should you care about perceptrons? Because classification problems are everywhere. Medical diagnosis, spam detection, face recognition, industrial sorting, autonomous driving, wildlife identification. All of these use the same core principle, and it starts with the simplest artificial neuron, the perceptron. In fact, ChatGPT, Sonnet, Gemini, every modern AI model, they are all built from millions of these connected together. The perceptron is the atom of artificial intelligence. Let's learn this using a classic problem, classifying iris flowers. Imagine a robot that needs to identify iris species by measuring their features. It scans the flower, takes measurements, and needs to classify it. There are three species we need to distinguish: versicolor, setosa, and virginica. They look similar, but there is a mathematical way to separate them. Before we dive into the math, here's where the inspiration came from: the biological neuron. Input signals arrive from other neurons. The dendrites act like filters. Notice how they have different thicknesses. Thicker dendrites let more signal through. They control the importance of each input. These weighted signals combine in the cell body, and if the total is strong enough, it fires an output through the axon. The key insight: the neuron learns by adjusting dendrite thickness, making some signals more important, others less. And that's exactly what a perceptron does with its weights. So let's move from biology to mathematics. Input signals becomes numerical inputs. Dendrite thickness becomes weights, numbers that control importance. The cell body becomes a weighted sum, or so-called total activation. Axon becomes the threshold function, and the axon terminals passes the output. This is a perceptron schema. And just like the brain adjusts dendrite thickness, a perceptron adjusts its weights. Each iris flower has four measurable features: petal length, petal width, sepal length, and sepal width. These four numbers becomes the input to our perceptron. Four features, four inputs. Each gets its own weight. Then we compute the total activation and we check if it is greater or equal than some threshold value to produce an output. But four dimensions are hard to visualize. So let's start simple, just one feature. We'll use only sepal length. This lets us see exactly what's happening geometrically. The measured value is our input, and it is multiplied by some weight to compute total activation. It is like calculating your final grade. Your exam score counts more than homework, so we multiply each by its importance before adding them up. And what exactly is this threshold function? We have 10 measurements of sepal length, 5 setosa flowers and 5 versicolor. The question is, where's the split? This is called a threshold function. It is like a switch that turns on at a certain point. As it slides along, it finds the boundary. Everything below this threshold is setosa, and above versicolor. The perceptron learns where to place this threshold. Okay, math time. But relax, it's just multiplication and addition. If you can calculate a tip at a restaurant, you can understand this. As an input, we have 7 centimeters of measured sepal length. The weight is 1, and it will remain unchanged for the purpose of this presentation. So the total activation is just 7. Mathematically, we can write it like this. Total activation is z. Now our threshold function checks: is z greater than or equal to some boundary? We can write this boundary as theta. So is z greater than or equal to theta? Since z is just x1 times w1, we have this equation. And here's the trick. We move the theta to the left side. Now we have minus theta plus x1 times w1 greater than or equal to 0. We clean right side, everything on the left. We can treat minus theta just like another weighted input. Let W0 equal minus theta and X0 equal 1. Why do this, you can ask? Because now the boundary is treated exactly like any other feature, just another weight to learn. We call W0 the bias unit. It's the adjustable threshold. And here's what our perceptron looks like after moving theta to the left side. A new input x0 always equal to 1, connected with weight W0, our bias unit. This is minus theta. Everything gets summed together. Bias plus all weighted inputs. This bias, it shifts the decision boundary, and during learning, the perceptron adjusts it just like any other weight. Same math for everything on the left side. This is our new schema of the perceptron. The input is measured versicolor flower with the sepal length of 7 cm. We mark it on the axis. Then we assume that theta is equal to 0, and we mark it also on the axis. The computation of total activation is as easy as that, and it equals to 7. In the threshold function, we have to answer the question, does 7 is greater than or equal to 0? It is, so the output from the perceptron will be versicolor. Second example. This time the measured setosa flower with sepal length of 5.1 cm. We can mark it on the axis, compute total activation, and answer the question, does 5.1 is greater than or equal to 0? It is, so perceptron will tell that this is versicolor. But in reality it is not. So we correctly classified versicolor at 7 cm, but failed on the setosa at 5.1 cm. So now what? How does the perceptron fix this mistake? That's where learning comes in. Here's our perceptron making predictions. But now we add feedback. Here's our training data. Notice the last column, the actual labels. In supervised learning, we know the correct answers during training. This error block compares the prediction to reality. The error flows back and updates the weights. That's how it learns. The error block receives two inputs, what we predicted and what was actually correct. The update is simply actual minus predicted, and we adjust each weight by adding this update. Simple subtraction. That's the entire learning algorithm. Let's see what happens when we are correct. Actual is 1, the predicted is 1, and the update equals to 0, no change. Same thing here, -1, -1, update is 0. When we are right, the weights don't change. When we are wrong, actual -1, but we predicted +1. The update is -2. We adjust the weights down. And the opposite, actual 1, predicted -1. Update is +2. Weights go up. The error tells us which direction to move the boundary and by how much. The perceptron only learns from mistakes. Now, here's the key insight. This update happens for all weights. So for our incorrect prediction, update is -2. Delta W0 equals -2. Delta W1 also starts with -1, -1, so -2, but we multiply by the input value x1. The weight update is proportional to the input. Why? As in our example, setosa with sepal length 5.1 was misclassified as versicolor. We don't just move the boundary by -2. We move it by -2 times 5.1. The bigger the input that caused the error, the bigger the correction. That's how the perceptron learns. We'll quickly go through the entire learning process for just different values. As you remember, for versicolor, our perceptron guessed right, so no weights update is performed. For the setosa, it was incorrect, so we have to compute the update. The new W0 will be just -2. Please note that in reality, all weights are updated. So we move the boundary to the right and compute total activation. Answer the question, does 5.0 is greater than or equal to 0? It is. Perceptron correctly guessed it is versicolor and no weights update is performed. Again, for setosa, our perceptron is incorrect, so we have to compute the new weight 0 and this minus 4. And the boundary itself is 4, so we moved it to the right again, compute total activation, answer the question, and Perceptron correctly guessed again, so no weights update is performed. For the setosa, even if the boundary was moved, we have to update the W0, and it moves boundary to the right again. So for the last iteration, or so-called epoch, the boundary is set to 6, and for the versicolor, as always, the perceptron classifies it right. And for setosa, the total activation is less than 0, so the perceptron classified the example correctly. Now we can tell that the perceptron learned the proper weights, so it will classify correctly each new incoming flower. And that's it. The perceptron adjusts its weights, example by example, mistake by mistake, until it finds the perfect boundary. You just learned the foundation of every neural network ever built.